Alright, here are these solutions to the review problems. Remember, try these on your own first. You should be working to get the solutions complete, and also check them on your own, and only then should you check the solutions and then rework to find any errors. I'm not going to go over the solutions. I will talk briefly about a couple of them that seem a little more challenging, but for the most part, I'm just going to be showing them to you. Alright, here are the answers to the first set of questions. Here we're just applying the derivative rules that we've learned. The product rule, quotient rule, chain rule obviously, which happens every time we take the derivative. Some trig functions, some inverse trig functions, logarithmic functions, exponential functions, so on and so forth. I've done a fair amount of simplifying here, so if your answer doesn't match mine, that doesn't mean it's wrong. It could be that you just haven't simplified fully. So go ahead and simplify through to check and make sure that your answer is correct. A couple to just mention a few things about. This here is sine cubed of x, which means that you're taking sine of x and then cubing it, multiplying it by itself 3 times. So I'm going to apply the chain rule there. E to the 1 plus natural log of x. I'm using the rule for e to the u, and then I do a fair amount of simplifying. My advice for simplifying is to remember that if you have something raised to a power, and the power is something plus something else, as it is here, you can rewrite that. Because remember, when you're adding the powers, that comes from multiplying 2 exponentials with the same base, and then you add the powers. And so after you take the derivative of this, you can actually use that to simplify, and you'll end up with e. Here, the variable that you're that you're differentiating with respect to is theta, and so you're considering theta as your variable in this situation, which is how you get this particular solution. I think that's about it for the most part. Just make sure you're organized, follow your protocol for taking the derivative, write down the rule you're using, label any functions u or v or both that are part of your original function, and make sure that you're very clear if you're taking the derivative or not, and so that you know whether you've taken the derivative yet. Okay, let's go ahead and take a look at a couple more. Alright, I'm going to go through the solutions to numbers 82, 83, 53, and 54. There's a minor typo here. This is actually page 189, so in case you were wondering, I did not totally lose my mind. It is page 189, 53, and 54. Those will be coming up on this, the upcoming slides. Here are the answers to numbers 8 and 9, taking the derivative. For both of these, you're applying the chain rule. In this situation here, what you're doing is you're taking this quotient, 2 minus x over 1 plus x squared, and raising it to the 1/2 power. So you're going to use the chain rule on the outside, and then the quotient rule on this inside piece here. And when I do a little bit of simplification, this is what I end up with here. Over here, again, using the chain rule, my variable that I'm differentiating with respect to is theta here. So I use the chain rule, take the derivative of the outside using the power rule, and then on the inside I'm using the quotient rule. And after doing a little bit of simplification, here's what I get. For number 10, I am going to take it and put it on the last slide. So if you're looking for that solution, stay tuned. Alright, well, let's go ahead and take a look at number 82. So for part A, we're going to take the derivative of this particular function to find y prime, and taking the derivative with respect to x, of e to the x plus e to the negative x over 2. What I did was I factored out the 1/2 and then took the derivative of e to the x and e to the negative x using the sum rule. So I took the derivative of each one respectively. Derivative of e to the x is e to the x, and the derivative of e to the negative x is e to the negative x times the derivative of negative x, which is negative 1. So I end up with e to the x minus e to the negative x. And what I did is I moved e to the negative x into the denominator, so it's 1 over e to the positive x value. And that's my derivative here. To find the tangent line, so part C, at the point x equals 1, first I need to find the value of y when x is 1. So I plug in 1 for x, that's what this represents here, y of 1. And I have e to the 1 plus e to the negative 1 over 2. I can type that in my calculator. It's pretty simple. I end up with approximately 1.543. So that gives me my point. Now I need the slope at x equals 1. Y prime of 1, using the derivative function that I found up here, is 1/2 times e to the 1 minus 1 over e to the 1. E to the 1 is just e. So finding that, using my calculator again, I get approximately 1.175. And then I use point-slope form, and after simplifying, putting it in slope-intercept form, this is what I get. For part D, I'm trying to find the normal to the curve at this point, so I need the opposite reciprocal of the slope that I found previously. So my slope is going to be negative 1 over 1.175, and that is going to give me negative 0.851. I don't know what happened here. Just ignore this piece. It looks like a negative. I don't know what happened. And so then when I use point-slope form again, remember I need to enter it into point-slope form again and simplify again, because when I use this new slope, I'm going to get a slightly different y-intercept. And so here's the function that I get. All right, taking a look at number 83. Here we are trying to figure out the domain for this natural log function. Remember, you can take the natural log of all positive values, because natural log is asking what must you raise e to the power of to get that particular value. And when you raise e to a power, no matter whether the power is positive or negative, you're always going to end up with a positive value because e is a positive number. So we need to make sure that 1 minus x squared is positive, meaning it's greater than 0. And solving for x ends up telling us that x must be, the absolute value of x must be less than 1. And that should make sense because this can't be negative. What would make this negative? Well, if x squared were greater than 1. So we must make sure that x is less than 1. In other words, the absolute value of x is less than 1, since I'm squaring it. So the domain are all x values less than 1 and greater than negative 1. Going on to part B, we're taking the derivative. F prime means we're differentiating with respect to x the natural log of 1 minus x squared. Remember, the derivative with respect to x of natural log of u is 1 over u times the derivative of u with respect to x. And here I have 1 over 1 minus x squared times the derivative of 1 minus x squared, which is negative 2x, hence the negative 2x. I want to know the domain of the derivative. And so here, notice my function, the derivative function, is just another function, and I want to know what the values that it is defined for. So a couple things to consider. The first is that f prime of x is defined so long as x isn't 1 or negative 1. If it's 1 or negative 1, then the denominator is 0. And we also know that, look, the derivative is just the slope of the original function. Well, you can't find the slope of a function if that particular function doesn't exist. So since our natural log function is only defined when the absolute value of x is less than 1, then the slope function, in other words, the derivative, can only be defined in this particular spot as well. So the slope is only defined when f is defined, and hence the domain of f prime is going to be the exact same as the original function. Remember, the only values that this didn't work for are x values of 1 and -1, but that wasn't included in the domain of my original function, and so I'm okay there as well. Number 53, this is a great review of continuity and differentiability. Remember, for something to be continuous, for a function to be continuous at a point, we need the limit as you approach from the left of the function and the limit as you approach from the right of the function to be equal, and you need that value to be equal to the value of the function at that point. This point is 0, so here we're taking the limit from the left as x approaches 0 from the left of f of x, and the limit as x approaches 0 from the right of f of x, and those two need to be equal and needs to be equal to the value of the function when x is 0. So from the left, I'm dealing with this sine plus cosine function. I take the limit as x approaches 0 from the left, and I can actually use substitution here. When I substitute in 0, I get something that's very nice, which is sine of 0 is 0, cosine of 0 is 1, and so I end up with just b, and b has to be equal to this limit, which is 3, and that's actually also equal to the value of the function, thankfully. So b has to be equal to 3. For something to be differentiable at a point, it means that the derivative as you approach that point from the left and the derivative as you approach that point from the right have to be equal as well. So here you can take the derivative of the left side, and the derivative of the left side using my trig function derivatives is going to be a cosine of ax minus b sine of x. And if you plug in 0 there, again, sine of 0 is 0. So you just end up with a times cosine of 0, which is a equals 5. Because the derivative as I approach from the right is going to be 5. Always, actually. And so the a value needs to be 5. Part C is a little tricky. Go ahead and read through this, but basically it's reminding you that if a function is not continuous at a certain point, then it cannot be differentiable. Remember that if something is differentiable, then it must be continuous, which means that if something is not continuous, then it will not be differentiable. All right, number 54, again, continuity at a point means the limit as you approach from the left of that point has to be equal to the limit as you approach from the right of that point, and that has to be equal to the value of the function at that point. So looking at the function f of x to the left of 0, that is where it's defined as sine of 2x. So if I take the limit as x approaches 0, I can actually use substitution again. Sine of 2 times 0 was sine of 0, and sine of 0 is 0. The limit of f as you approach from the right, well, it's defined by the function m times x, and I can use substitution once again. I'll get m times 0. Now notice I've written this out because I want to notice something important. I'm trying to figure out what m has to be. Well, the value of the function at 0 is sine of 0, which is 0. And so notice that m can be anything, because if it were any number and I multiply it by 0, I end up with 0. So m can be any real number and the function will still be continuous. Now looking at part B, to be differentiable, it's a little different, right? It's not just looking at what the value of the function is approaching. It's actually looking at how that function is approaching that value. In other words, looking at the slope from the left and the slope from the right. The derivative of the function to the left of 0 is going to be 2 cosine of 2x, and the derivative of the function as you approach from the right is just going to be m, using the power rule. And so when I plug in 0 there, I have 2 times cosine of 2 times 0. Cosine of 0 is 1, so 2 must be equal to m, and so in order for the function to be differentiable, the value of m must be 2. Alright, so here's the situation for number 10. We have a particle which is moving along the y-axis, and its position along the y-axis is given by this function y of t. And it's important to remember that y of t is telling you the position where the input variable is t. So you can imagine the particle moving along the y-axis but this isn't actually the graph of the function y of t, right? It's important to know that this exists on an axis where the horizontal axis is time, and its actual position on this y-axis here is determined by that function. If I want to find the velocity, I need to take the derivative of the position function, and to do that, I differentiate with respect to t, the function t times e to the negative t. I'm going to use the product rule here. So I'll have t times the derivative of e to the negative t. Derivative of e to the negative t is e to the negative t times negative 1, which is why I have negative out front. And then I have e to the negative t times the derivative of t. Derivative of t is 1. And simplifying this, I have an e to the negative t. I can pull that out front, make it 1 over e to the t, and then I will end up with a negative t plus 1, or 1 minus t. Then finding the velocity when t is 1, I have 1 over e times 1 minus 1, which is, of course, 0. Interpreting what this means then for part B, because it asks when is the tangent line to y of t going to be horizontal? Well, that's when the derivative has a slope of, when the derivative is equal to 0. In other words, when the function has a slope of 0. And as we saw, this happens when t is equal to 1. And what you can also tell is, since this is the velocity, that means that when t is 1, the velocity is 0, which means the particle is at rest after 1 second.